Hello, this will be a demonstration of Proposition 3 from Book 3 of Euclid's Elements, which states that if in a circle, a straight line through the center bisects a straight line not through the center, it also cuts it at right angles. And if it cuts it at right angles, it also bisects it. The peculiar thing about this proposition is that it's its own converse. We usually don't see this. Usually a converse is its own proposition, but here they're pushed into one. It's no matter though, it doesn't throw its truth into question or doubt, so let's continue as normal. All we are given is the circle ABC, like so, such that we have a straight line not through the center, AB, being cut by a straight line through the center, CD, and let's say it cuts it at point F. And now either CD bisects AB such that AF is equal to FB, or CD cuts AB at right angles such that the angles at F are right angles. Now, if it bisects it, it also cuts it at right angles. And if it cuts it at right angles, it also bisects it. So this is what we are going to prove. We're going to prove two things, actually. Now, if we start with the first case, if the straight line CD bisects the straight line AB, we shall take the point E as the center of the circle ABC, like so. We can do that by proposition 3-1. And then we shall join the straight lines EA and EB. We can do that by postulate 1. Now we know from our given that AF and FB are equal. We're dealing with the case where CD bisects AB at point F. So we know that AF and FB are equal. We also know by definition 115 that because EA and EB are radii of the same circle, they're also equal. So we can say that EA equals EB. And we have this third side, EF, which is common, so that we can say the two triangles EAF and EFB are equal in all respects. The important respect here being that the angle AFE is equal to the angle BFE, and these angles being adjacent and equal means that they are right angles, which means that CD cuts AB at right angles, and so we have proven the first thing we set out to prove. Now, moving on to the next case, if in the circle ABC, we have the straight line AB, not through the center, and we have the straight line CD through the center, cutting it at point F, such that the angles at F that CD makes with AB are right angles, we shall also say that AB is bisected by CD, namely that AF equals FB. Again, we shall do the exact same construction. We shall take the center of the circle ABC as point E. We can do that by proposition 3-1. And again, we shall join the straight lines EA and EB by postulate 1. Now we know that EA and EB are equal, and these two straight lines being equal, they're equal because of definition 115 again. These two straight lines being equal, they're also in the triangle EAB, and so the angles which they subtend, namely EAF and EBF, will also be equal by proposition 1-5, and so we can say that the angle EAF is equal to angle EBF. Now we have the straight line EA equal to EB, again by definition 115. We also just proved in step 4 that the angle EAF is equal to the angle EBF. And furthermore, we know that the angle AFE is equal to the angle BFE because both are right angles and all right angles are equal to each other by postulate 4. And so we have in a triangle two angles equal to two angles, and the side subtending the equal angles also equal. So by proposition 126, we can say that the triangles are equal in all respects, namely that AF be equal to FB. Now we have finished what we set out to prove, and so the proposition is done. Therefore, etc. QED. Again, peculiar thing about this proposition, it's its own converse, which should not surprise you from here on out. So that's all I have to say about this proposition, and so I shall move on to proposition 3-4.